Welcome to another episode of the Training Data Podcast. My name is Jake Shermeyer, and I'm going to be filling in for our usual host, Ryan Lewis, today. I am a research scientist with CosmiQ, and I was also the challenge manager for SpaceNet 6. Today, I'm being joined by a wide host of characters here. First of all, we've got data scientist from CosmiQ, Daniel Hogan, also known as the Prince of PyTorch to some. He has led the development of the most recent addition to Solaris. We'll be talking a little bit about that today, as well as the SpaceNet 6 baseline, and was the visionary behind the new SpaceNet 7 metric. How's it going, Daniel?
Doing well. Good to be here.
Thanks. Also joining us today, we've got Ronny Hänsch. He's a senior researcher with the German Aerospace Center. I believe our first German to join the Training Data Podcast. He is one of the leaders of the IEEE GRSS Geoscience and Remote Sensing Society, which is also a SpaceNet partner. Ronny has expertise in remote sensing, multiple publications focused on SAR, data fusion approaches. That's a hint to what we'll be talking about today as well. So welcome, Ronny.
Thank you. Happy to be here.
All right, and our final guest today is a community enablement engineer for Capella Space. He has also co-authored a few blogs with Daniel Hogan, our SAR 101 and 201, as you might remember. He also has expertise in remote sensing and image processing, focuses on computer vision overhead observations, notably SAR. And his name is Jason Brown. Welcome, Jason.
Thanks, Jake, and good morning, everyone.
All right. Well, thanks, everyone. So the reason why I brought this cast of characters together is we've really got an omnibus episode. If this podcast was a movie, we like movie references here, you might think of it as Pulp Fiction, because we've got many different storylines coming together, many different modalities as well. As this is a SpaceNet 6 focus podcast, this is going to focus on kind of the intersection of SAR and optical imagery. So a lot of our storylines today will really focus on that intersection. So we'll be talking about the data fusion and also transcoding SAR to look a little bit more like optical data. We'll also be discussing the value of frequent revisit. We can actually have many revisits from our SAR sensor, and ultimately that will have some benefit for when you're trying to map objects like buildings. And finally, we'll be talking about the SAR library that Daniel led the creation of. So this is well, it's not only a SAR library, it's also a remote sensing pre-processing library, and it also has a new API for really seamlessly stringing together different operations. So all of these topics we'll be discussing today. If you're not familiar with SpaceNet 6, you can go back and listen to some of our past episodes or read our blogs about this. But the gist of SpaceNet 6 is that it's a unique data set that features a combination of Capella space SAR data and Maxar Worldview 2 imagery over the port of Rotterdam, the Netherlands. And we had a challenge around this, and the goal of the challenge was using AI and computer vision algorithms to automatically extract building footprints at scale. So let's just jump right into our first topic here, and that's really discussing data fusion and transforming SAR data to look a little bit more like optical data. So on the data fusion front, why would we do data fusion? Well, there's obviously advantages to both of these modalities. So using both SAR and optical together is likely a wise approach to try to extract different features of interest. The second topic is really the transcoding or transforming SAR data to look a little bit more like optical data and steal some of that good color that optical data has. So why would you do this? You would do this maybe because you don't have concurrent optical SAR collect. You might only have SAR imagery at one date, and you might have optical at another date. So can you use that optical imagery in some way to attempt to colorize or improve your SAR data in some way? And furthermore, will that help you with your task of interest? So we really teased or touched on some of this with our baseline. And we did that with a transfer learning approach. Daniel, can you walk us through kind of what transfer learning is and how we did that with the baseline?
Yeah, so with SpaceNet 6, we faced, it was constructed to be exactly the type of challenge that you're describing, where you have different modalities from the same place, possibly from different times, although in SpaceNet 6 they were coincident. And so we addressed this with a transfer learning approach where the model was first trained on optical data for the area in question. And then the final weights from that process were used as the initial weights for the subsequent training on the SAR data. So the idea is that since the SAR data was limited, we could use the optical data to teach the model the basics of understanding basic shapes and lines and the nuts and bolts of identification and segmentation in this overhead imagery. And then once that had been done, the model could hone in specifically on looking at the SAR data that we had in this data set.
Yeah, that's interesting. And this transfer learning approach, this helped us, I'm assuming, extract buildings a little bit better versus just training on SAR?
Yeah, so compared to a model trained only with the SAR data, a model trained with the initial transfer learning step with the optical data did perform noticeably and statistically significantly better.
Okay, that's interesting. Now, I know a number of our participants tried the same approach, but it was interesting, only 2 of the top 5 ended up doing a similar approach where they pre-trained on the optical data and then on the SAR data, and they found that training on ImageNet instead upfront ended up being equally performant. So that's an interesting statistic. Perhaps that tells us that maybe just pre-training on ImageNet would be an acceptable alternative when you don't have optical data. However, I still believe that there might be some value here that really requires some further research beyond just the challenge setting. So the next topic I want to talk about here is data fusion. So fusing both optical and SAR data. And in one of our latest blogs, Jason and I collaborated on a little bit of this. Jason, can you walk us through some of the traditional data fusion approaches you might try to take or attempt with SAR and optical imagery?
Yeah, certainly. So in general, you can think of it as a transform. We're going to transform the optical imagery and the SAR imagery into some other space, mix them there, and then do the transform back into the original space. So for instance, you can do the same thing to do with SAR fusion as you do with pan sharpening. And that's the approach I took here. You can, if you know anything about pan sharpening techniques, there are several. And the one that I used was the hue saturation value method. And that gave me the best results. But the idea is you would transform the RGB imagery into the HSV, hue, saturation, and value space, and then replace the value, which is also sometimes called intensity, with the SAR image, and then transform it back into an RGB. And that was pretty successful, and in your blog post, you show several examples of that. But the idea is basically you take both SAR and optical imagery, transform it, mix them, and then transform it back, and that provides the fusion.
Yeah, and it was interesting how well this worked in the sense that you could really maintain the really valuable structural components of SAR. So how different things appear in the SAR image space, but also add in this really vibrant splash of optical color. So what we think helps in terms of computer vision models when you're trying to detect building footprints is that color really can help you discriminate between things that are, say, forest versus things that are buildings, just because you've got some green there versus other colors for buildings, such as your grays, your reds. But beyond that, we've really had a lot of other research that's starting to grow, at least, where we do this SAR to optical image transcoding and translation. So that basically means we're training a deep learning model or some sort of model to do this process automatically, and maybe apply that in a situation where we really don't have that concurrent SAR optical collect. And Ronny, you've got some good experience with this. Can you walk us through some of the approaches that have been done so far?
Yeah, sure. I can try. So the idea is that SAR is actually quite nice data, right? So we can look through clouds, we can run it during the night and so on. But one of the disadvantages, as you mentioned, is it's really hard for humans to interpret. So there's, for example, no direct visualization. You always need to have some kind of projection into a color image. Then the image geometry is different, and a lot of effects are inside of the SAR data, which people don't really know from optical data, like layover effects, speckle, orientation-dependent backscattering, and so on. So there are a lot of approaches that try to transform a given SAR image into something that looks like an optical image of the same scene, so that it's a little bit easier to interpret for humans and maybe also for machines. The problem here is early works tried that with regression, but that usually does not really work well for this purpose because the problem is really ill-posed. Usually there are a couple of viable options, so how you could take a SAR patch and transform it into an optical one. And what regression tends to do is to compute the average of all of those options, and then you don't really get nice results. Mm. The most of the successful approaches today use actually generative adversarial networks, or GANs, which consist of a generator that tries to create a realistic optical image given a SAR image, and then a discriminator that aims to distinguish between an actual optical image and a synthesized optical image based on the SAR data. Now, GANs come with their own problems, of course. So a vanilla GAN, for example, you need paired data, so a SAR image and an optical image that are aligned. They are a little bit tedious to train, as convergence is really hard to measure and they oscillate a lot. And often they don't really generalize that well for out-of-distribution data. But in contrast to pure regression, a GAN can decide between one of the options instead of computing the average. So there are a couple of works doing that, and the results are really quite impressive. So you can really take a SAR image and produce something that looks really like an optical image for a human observer. You need to be a little bit careful when you're interpreting that. For example, if you have, let's say, some flowers on an agricultural field, the blossoms might be open and then they have a color, for example, yellow, or they might be closed and then it's just green. So now in an optical image, you would see that. But let's assume in a SAR image, this part is not really represented in the signal. So you can't really tell in the SAR signal whether the blossom is open or not. Now, the GAN will have, in the best case, recognize this is this particular field of this kind of plant, but there's no way it can tell whether the blossoms are open or not. So what it will do is randomly decide for one of those options. And that might cause that if you do that, that you have yellow fields during a time where this flower usually doesn't bloom. And this is just one example. There are a lot of this kind of problems. So if you interpret these transcoded images by a human, you need to be really careful. But a different line of research is actually just using this as a byproduct. So the idea is that to do that, you only need to have paired data, right? So an optical image and a SAR image. You don't need to have any kind of semantic knowledge. But if the GAN is really successful in synthesizing the optical data, it means that it needs to be able to distinguish between different semantic classes. So it needs to implicitly recognize this is a city, so I need to synthesize the texture of a city, or this is a forest, so I need to create the texture of a forest. So this means the features that the GAN is learning in order to do that, they're really interesting and really meaningful, and then they can be used in a supervised learning setting as an input to a classifier, which you train on labeled data. And the trick is then those features are already well defined in the self-supervised part. You don't need this much label anymore in the training data. So you can cope with much fewer labels and you still get much better results than you would get when you train the supervised learning network from scratch. And that's pretty cool.
Yeah, that actually is really cool. I mean, so this, as Ronny describes this is really interesting work, but this is very cutting edge stuff, because right now we still need a lot of custom models. You have to build these things from scratch for each individual task. But I think what he's describing is very promising, because if you can do this, if you can build a GAN to understand the semantic information, the task it's ultimately going to accomplish. So in our case, it might be extracting building footprints. Ronny's describing kind of a land use mapping scenario where you would do that. I think ultimately that can be a really powerful tool to transform your SAR data and leverage it in the best possible means to really also incorporate that optical imagery, bring those things together, and then ultimately do your task of interest. So I'm cautiously optimistic that type of research can continue to grow here. A lot of that has really occurred with Sentinel imagery, correct, Ronnie?
Yeah, so Sentinel has the advantage that it's giving you a SAR image from the Sentinel-1 satellite and an optical image, or actually a multispectral image from the Sentinel-2 satellite. And you can basically geocode them, and then they're already more or less aligned. So this is a big advantage.
Yeah, so I mean, that's Sentinel is obviously a wonderful resource. The advantage of the SpaceNet data set, of course, is that we're going to have much higher resolution. So I think really attempting some of these techniques at that very high resolution can be particularly interesting, because I don't think a lot of that work has been done. The way SpaceNet is permissively licensed, that will also hopefully open up further research avenues. And that's really some of the research we're trying to incentivize by open sourcing these data sets. And I think we should hopefully have some success with that in the future. So is there any other future research paths or potential topics that anyone could find interesting to do with the SAR or optical combinations?
Yeah, Jake, going back to the transform methods, something that I'm interested in pursuing is looking at Fourier methods to do the fusion. I don't think there's been a lot going on there, and I'm developing a process right now to do that. And I think, given the nature of SAR, it should be better than just sort of the naive HSV transformation.
Yeah, that's interesting. That would make some sense going into the Fourier space. And,
I'm also curious if Ronny has run across that at all.
To do what exactly?
Basically, in doing the fusion using a Fourier transform rather than, say, a principal components or a HSV.
I see. Well, the most recent work I have seen was a CVPR paper from this year, where they tried to do domain adaptation by transforming the data from the source domain and the target domain into the Fourier space, in the frequency space, and then exchanging part of the low frequencies of both domains and then transform it back. So they did that not with multi-sensor data, but with street view data. The source domain was daylight images, which you usually have in abundance, and the other one was images during sunset or dawn, where the scene is much darker. And there they showed it actually worked pretty well. I think it would be curious to try that with SAR and optical data.
That's cool. Yeah, so I do want to kind of summarize some of the stuff we tried with our first blog. This was very preliminary research, but ultimately it didn't work very well. So the data fusion itself worked very well. It provided a significant performance boost over the SAR data alone. But when we tried to recreate the data fusion process by transforming the SAR data to look a little bit more like the optical imagery, using a GAN, in this case we used the PIX-to-PIX network, ultimately that didn't work very well. And I think the reason for that is it kind of touches on some of the things that Ronny mentioned here, in the sense that the GAN didn't really have an understanding of the end task that we're trying to do. It was just trying to make the image look much like as much like the optical image as possible, but it didn't really understand that ultimately we're going to use this for building footprint extraction. I think some further or additional inputs into this process would probably be best. We used a SAR span image, which is the total scattering power. It would probably be best to use quad pole data. It would probably be best to use maybe some complex inputs. And that's something we'll probably ultimately end up being released in a expanded data set, the expanded SpaceNet 6 data set, which we'll talk about at the end of this podcast. So moving into topic 2 here, one of our other research blogs in this series really focused on the value of revisit for SAR data. And revisit in this case means we're re-imaging the same locations multiple times. And the SpaceNet 6 data set over Rotterdam, interestingly, has on average about 15 revisits to the same locations repeatedly. So can we use those revisits in some way to improve our model's performance? And what we found is that revisit really helps you quite a bit in terms of extracting building footprints. If you have multiple looks of the same areas, you can have predictions created for each of those areas, and then you can actually aggregate those predictions together and kind of average your predictions. And we found this produced about a 20% boost in our overall performance, so quite valuable here. But that did peak at about 4 revisits. So 4 ended up being the magic number. Anything beyond that really didn't help us improve performance. There's a few reasons for that, but I think the first reason was really that we end up having multiple looks from, say, the north and the south facing. You can average those together, and that ends up being a more accurate ground truth building footprint. The 4 is the magic number, I think, just because you end up having 2 revisits, 2 from the north, 2 from the south. That adds some boost, but ultimately ends up not really adding much more beyond that. So, Jason, can you talk a little bit more about some of Capella's future capabilities? I know that you guys are planning to have some frequent revisit rates.
Yeah, that's right. So right now the plan is the 36 satellite constellation to provide hourly revisit anywhere in the world, right? And so, as you could tell from the Rotterdam dataset and the work that we've been doing here, the hourly revisit gives you some very interesting results and opportunities to do things such as activities-based intelligence, things like that. Going back to your other point, though, real quick, about the multiple looks, I'm kind of curious too to see in the future if different geometries would help that. You know, for the most part, we had the same look angle, the same incidence angle, and so that sweet spot was 4 looks. But I wonder if it would help if we had a diversity of geometry there, improving that, or to improve the building footprint.
Yeah, I think that's certainly plausible, and I think we're all excited to have Capella's constellation up there and really be able to use some of this data in the future, and hopefully we can start to test things like that. Because I do agree with you. I would think that having multiple look angles, particularly from like a north facing or south facing or east or west, looking at an object from 2 different directions and seeing different sides of it, I think that can be particularly valuable for really improving our performance for tasks like this, particularly for static objects.
Yeah, certainly. And there's some research being done where folks are trying to fuse the 2 different look angles to get information for, say, both sides of a tall object, right? And then you can see, oh, the layover occurs this way, but then the shadow, what's on the other side? What's in that shadow? So they fuse both sides. And that probably could help out in terms of building footprints, just to be able to avoid the layover that occurs.
Yeah, absolutely. I think that's very interesting. Could be a valuable area to explore further here in the future. So with that, does anybody else have any comments on revisit? Otherwise, we can move into section 3 of this multimodal extravaganza. All right. Well, without further ado, then let's talk about our new library that has been added to Solaris. So, not familiar with Solaris? Solaris is a software package written in Python that CosmiQ has led the creation of, and it's really all about both pre-processing and post-processing remote sensing data to be fed into a deep learning pipeline here. And Daniel Hogan has been our lead on Solaris. And he has actually created a new library. So Daniel, can you talk about this new library you've created?
Sure. So the new library is a pre-processing or post-processing library for getting imagery to the point where it's ready to be tiled and fed into a deep learning model. And it consists of a variety of different functions for processing images and also labels and associated data. About 60 classes in total, but the part that's germane to what we're talking about today is about 1/3 of those are focused specifically on working with SAR data and implementing some of the special pre-processing algorithms associated with SAR.
Okay, Awesome. Well, that sounds really powerful. I mean, is there anything out there in the open source like this?
There are SAR libraries out there, but there is nothing that combines everything in quite this way of SAR tools with data cleaning tools with really the whole package for everything you might want to do in creating a data set, particularly when creating a multimodal data set where these kinds of data preparation and data cleaning tasks come to the fore.
Okay, that's interesting. So beyond that, you also introduced a new API called PipeSegment. Can you walk us through what that is and the advantages of that?
Yeah, so what makes the pre-processing library more than just a random collection of Python functions is that all the classes in the library derive from a base class called PipeSegment. It's in the PipeSegment module. And what this class does is it does a lot of the work behind the scenes. And in particular, it makes it easy to combine the different classes together to construct more complicated custom use classes. All these classes become just building blocks from which one can create a workflow of arbitrary complexity for a pre-processing pipeline.
Yeah, and I mean, I think a lot of remote sensing workflows really are stringing together operations one after another. And I think that this PipeSegment will really help streamline some of that process, correct?
Absolutely. Basically, the way it works is for whatever task you want to do, you kind of picture the flow chart of how the different operations relate to each other. For each block in the flow chart, you write one line of code, basically picking out the class from the library that does what you want that block to do, and all the common tasks are already there. You can, of course, add a new class if something's missing. But once you've done that, the next part is to specify how the inputs and outputs of all of the classes relate to each other, how it all connects together. And this is where PipeSegments becomes very powerful, because you can do all of that in one line of code using a very concise notation, and it leads to faster and easier construction of these workflows.
That's awesome. So if you want to try this out right now, this is available on our GitHub, correct?
It is. It is available on the Solaris GitHub. There is a 3-part tutorial in the Solaris documentation, and we have a video tutorial as well.
All right, good stuff. So that means this should be fairly easy for you to get started on as well, which means it's a lot less intimidating, which is always a good thing when you're trying to take on a new project or try to implement some new code. So that's all very well and good. So the last thing that I really want to talk about today is the expanded data set. So SpaceNet 6, we're planning to roll out an expanded data set. So Daniel, can you walk us through what we're planning for the expanded data set release?
Definitely. So for SpaceNet 6, we released data that was processed and tiled and kind of ready to go, which was what was needed for the competition. But we also want to open up the possibility for people to try their own ways of manipulating the data and working with the data more broadly. So what this data set, this expanded release is going to be, is it's still the original data from which the SpaceNet 6 data set was constructed. But what's going to be released this time is the full image strips. All 204 image strips collected over Rotterdam, the original data in range and azimuth coordinates, complex values, all the phase information there, intact, ready for people to experiment with and try new things.
Yeah, that's awesome. So, I mean, I think this is probably going to be the first data set really of its kind with this kind of licensing at this type of scale. So it's really exciting, and I'm optimistic that this will really stoke some new research in the future. So maybe you give an example of something you could do with our new library and the new complex data we might be releasing.
Sure. So there are lots of decisions that one makes along the way in going from complex data to a finished product as you might feed into a deep learning model, for example. Things like, do you want the multi-look to have a smaller, large kernel size? Do you want tiles to be smaller, large? You know, I think we made a reasonable set of choices in constructing SpaceNet 6, but now people can try everything. They can try out different things and see how well they work. And even something as basic as, what information are you looking at? So for example, for each pixel, do you want to look at a single magnitude, or do you want to look at 4 magnitude values for the 4 different polarization combinations that are there? Or do you want to look at something completely different, like incorporate the phase information, which you could do with different kinds of polarimetric decompositions. There are 3 polarimetric decompositions ready to go in the pre-processing library. So if that's something you're interested in, then that would be one of many cases where the pre-processing library is a real good tool to use.
Awesome. So anybody else have any other interesting research areas they might want to play around with the expanded data set?
There's been some research done in using complex data to do object detection. That might be an interesting route to follow.
Yeah, absolutely. And on that note, I do want to point out that the SpaceNet 6 dataset is loaded into Xavier's tool Groundwork. So that means you can annotate any features that you might be interested in. So there's a lot of boats moving around in Rotterdam. I think you could really have some fun annotating boats and then trying to do some object detection with the complex data. Would recommend that if you're interested in a research area.
You know, Jake, we also forgot to plug our little GitHub repo for the colorization fusion stuff.
That's right. Yeah. So on the SpaceNet Challenge GitHub repo, we have a code base up there where you could do the colorization that we did in the most recent analysis blog there. Also on this GitHub repo, something we forgot to plug is the top 5 winners of the SpaceNet 6 Challenge. Their prize-winning algorithms have all been uploaded to that GitHub, so you can download those and use those today for building footprint extraction, or modify them in any way you really want to work with SAR data or overhead observations, which is, I think, a great resource for people trying to get started with this. So I think that brings us to really the end of this podcast here. So in summary, we talked about quite a few different topics here in this multimodal extravaganza, including the data fusion approaches, translating SAR data to look more like optical data, and ultimately the SAR new library we're releasing, as well as the expanded SpaceNet 6 data set. We have a couple of events coming up here that I want to make people aware of. The first of which is the IGARS 2020 conference, which will be running from September 26th to October 2nd. The registration for that is very expensive, correct, Ronnie? How much is the registration?
Well, it should be around $10, so I hope that is affordable for most of the people.
Yes. So there'll be a lot of great content there. I would recommend checking out one of our papers that we wrote. It was on use the SpaceNet 4 data set, which you might remember is a multi-look data set. So we've got 27 look angles. How does different look angles from extreme off-nadir really affect your ability to detect road networks? And that was the focus of this paper. So we fuse all 27 together. How does that help you? If you're just using one of these or a few of these, how does that help you? So ultimately, as you might expect, road network detection gets fairly tricky as you move off nadir, but really in those mid-nadir ranges from 0 to 35 degrees off nadir, it's actually quite easy and works quite well with our approach. So I'd recommend checking that out. Another thing coming up as part of that conference is a panel that I'll be participating in on September 2nd, 2020. That's at 12 p.m. Eastern time. So that'll be 9 a.m. West Coast or 6 p.m. Central European, if you're doing all the math there. And that's called Deep Learning and Remote Sensing, Challenges, Solutions, and What Makes Us Different. So if you're interested in really diving deeper into some of the complexities of remote sensing, computer vision, check me out. I'll be on that panel with a number of other really interesting guests if you think I'm interesting. But anyway, I think we'll leave it there. Thank you to all of our great guests today. And I think this was a really interesting podcast that should have some good insights for a wide range of people interested in these topics. So with that, I will say goodbye.